Okay, welcome back everyone. So today I'm going to be making a video on Taylor series and Maclaurin series. So I have in the past made a video on Taylor polynomials, so approximating non-polynomial functions with the Taylor polynomial, but I didn't really cover Taylor series. And I actually want to make a video where I employ these at least the Maclaurin series, but as well, I can just directly tell you right now. So Maclaurin series is basically just a special case of Taylor series, where that particular function representing the non-polynomial function is centered at like 0 essentially, and I'll show you what that means. So the idea is basically this. So if we take some f of x equal to, and suppose f of x is some function that we want to define using Taylor series. Suppose this is some x minus c, or yeah, sure. So okay, I'll do it like this. So we'll call this a sub 1 times x minus c. Actually, this is our constant term. So we could call it c sub 1, which might be better. So we have c sub 1 plus x minus c times c sub 2 plus x minus c squared times c sub 3, and so on. It's probably better to actually put these in front, so it doesn't matter, but it looks nicer because the constant term usually goes here. And all the way to plus, I'm just going to rewrite this because it's really aggravating me. So just real quickly, plus c sub 2 times x minus c plus c sub 3 times x minus c squared, all the way to plus c sub, well, this is actually an infinite series, right? So we go up all the way into infinity, so it just goes on like this forever, okay? Okay, and essentially what we want here is, in order to get as good of a representation for f of x as a polynomial, the idea here is that we want all the derivatives of f of x to match up with this polynomial. And that includes the 0th derivative. So we need f of, and the center in this case would be c. That's the center here. So in this case we would be looking at f of x, I guess, around c. That is our center, okay? Okay, so we actually need, basically, here's the idea. We need f of 0 to equal this thing. Or, yeah, so we need whatever f of 0 is for our non-polynomial function, we need that to have the same value as this polynomial here, okay? And we also need f prime of 0 to equal blah blah blah, and f double prime of 0, or f double prime at 0 to equal blah 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 blah. And for notation we use this here, like the sigmalizing the 3rd derivative at 0 equals blah blah blah, of course. So that's the idea here. Okay, so what happens when we actually take the derivative of this and add 0? So think about the derivative. So okay, let's just consider, I think the best way to do this would be to do this with an example. I did it last time, but okay. Anyway, to get an idea, consider the first derivative of x, okay, f prime of x. That's just going to be, well, here that's just going to, the first term in this case is going to be c sub 2 plus, here it's going to be 2c sub 3 x minus c. And chain rule here, well, the derivative of the inside is 1, so that's why I'm not doing anything there interesting there. Yeah? Plus, obviously that's just going to be 3, right? That's going to be the next term, times c sub 4 times x minus c squared, and this just goes on forever. So, okay. And the second derivative is similar idea. And at 0, notice at 0, all of the terms with x, or at c for that matter, all of the terms with x, okay, this is the idea. If we take f prime of c, which is our center, and that's what we're focusing on, we want at our derivative near c, around c, to be equal to our polynomial function. Okay? This, all of the terms with this value, with this term here, x minus c, will go to 0. So that's literally all of the non-constant terms. So the constant term is the only one that survives, which is c2. So we need f prime of c equals c2. Okay, so that's pretty nice, right? But it doesn't always work this nicely. So, okay. So now if we consider f double prime of x, that's just going to be, well, 2c3 plus 6c4 times x minus c plus, and goes on forever, of course. Okay, and consider this at 0. Same idea, right? This 2c3 is the only term that survives. But now we have a 2. And notice that there's a 1 here, okay? 1 times our c2. And there's a 2 times 1 times our c2. If we continue to the third derivative, we'll see a pattern, okay? And a reasonable one at that, if we look at the nth derivative, which I'll show you in a second. Okay. So the third derivative, just take the derivative of this, we just get, well, we get 6c4 plus, and then some other stuff, right? And, yeah, so some other stuff which doesn't really matter, as we know, because that'll just become 0 when we plug in c. So this is the only term that will survive when we plug in c to our function, which is what we're focusing on. But notice that this is just 3 times 2 times 1. You might notice a pattern here. It looks like our nth derivative will just be n factorial. We'll just have an n factorial here in some c sub n minus 1, c sub n plus 1. Look, so for the third derivative, we have c sub 4, and we have a 6 here, which is just going to be 3 factorial, right? And if we take a look at the nth derivative, and I need you to think about this, the nth derivative, all of the terms before it, well, they will go away, right? Because the nth derivative of something to the nth power. So consider like our nth term here. So that would be c sub n of x minus c to the n plus, so continues, plus like n plus 1, the n plus 1 term, and all of this will go away because then this will become a constant. And if we keep applying derivatives here, you'll see that this will just become n factorial. It'll be just, the constant here will be n factorial times c sub n, right? And all the other stuff, well, we're just plugging in c, right? So that'll die. So in other words, it's pretty obvious that our nth derivative at c, okay, well, we don't really need that yet. The nth derivative, okay, well, I mean, we don't really need the nth derivative, we just need the nth derivative at c, that's what matters. So, just don't worry about that stuff. The nth derivative at c is equal to, well, n factorial times x, what am I doing? It's just gonna be c sub, just making sure, so yeah, so actually the term that survives here, it's actually going to be c sub n plus 1. Doesn't really matter here, c sub n plus 1. Doesn't really matter what we put here, to be honest. That's a bit aggravating. Oh well, just making sure that, we did that correctly. Okay. Usually you just use, for the first term, you use like c sub n, c sub naught, c sub 0. So let's just say we started off with c sub 0, c sub 1, c sub 2. Okay. So that way it would be c sub n, because that's just much nicer. So then we have c sub 2, c sub 1, right? C sub 3. That way it's much nicer, right? We just, okay. C sub n, right? And of course, times n factorial. This is my point here. So c sub n times n factorial. And really, now all we're really trying to find are the constant terms. That's the goal here. We want to find our c's such that will equal our function, our non-polynomial function. Our non-polynomial function will equal our function, the area around our polynomial function, around, area around c. And we want coefficients that will allow for that to happen. So in other words, this implies that our coefficients, the nth coefficient, is just going to be the nth derivative at c over n factorial. And this is the key idea, okay? This takes a while to explain, but it's a very key idea, okay? And how do we express this as a series? How do we express what we've just found as a series? Because, okay, so, it's pretty easy to see. If we want to express this as a series, and this is the definition of Taylor series. So Taylor series, our function, f of x, non-polynomial function, equals around c, centered at c, right? That's the, so from n equals 0, okay? From n equals 0 to infinity, that's about infinity, okay? Of our c sub n times, c sub n times x minus c to the n. This is literally what we have here, right? That's what we put here. But we found our c sub n, right? Our c sub n is this here, so why don't we plug that in? So we have the nth derivative at c over n factorial times x minus c to the n. This is Taylor series. And with that, we're pretty much done, because Maclaurin series is the case when c is 0, okay? It's when the function is centered at 0, so that's our nicest case, right? We don't get this ugly thing here. So Maclaurin series, I'll write that for you right now. Maclaurin series for some function f of x centered at 0, we get Maclaurin series of that function equals 0 to infinity of the nth derivative at 0 over n factorial times x to the nth power. Okay, so that is the end of this video, and I think I'll make a video in just a second about this really exciting thing that I actually, hopefully you're actually able to see that part of the board. Okay, it's fine. And hope you enjoyed that video. I'll make a follow-up video for a very interesting concept, and that's just going to be a quick derivation of Euler's great formula. Okay, so I'll see you in that video. Hopefully you enjoyed, and goodbye.